So I hope my audio is clear and screen is visible. Right? So we shall proceed, right? Can you please confirm, am I audible? Professor Sudeep, are you here? Okay. All right. So I'll start. I don't know. Nobody is here right now. So it's 6:02. I'll start. So in today's lecture, we will cover genetic algorithms, linear programming, and integer programming. So in the previous class, we have discussed meta-heuristics, and in that class, we discussed about single solution meta-heuristics. Now we will see what are population-based meta-heuristics, and genetic algorithm is an example of population-based meta-heuristic. Okay, so we'll talk about population-based meta-heuristic. So this is the short form of writing this population-based meta-heuristic is P-Metaheuristics. This is a high-level template of a P-Metaheuristic. So Professor Sudeep, are you here?
Yes, I was having some problems, so I was trying and
Okay, no problem.
yeah. So some network issue probably was there, so I was unable to join.
Right. So okay.
Yeah. Sorry. Yes.
So I had just started talking about meta-heuristics. So in the last class, we were talking about single solution based meta-heuristic, and we saw local search and simulated annealing. And we couldn't complete population based meta-heuristic. So population based meta-heuristic. So genetic algorithm. So in this lecture, what we'll cover genetic algorithm, linear programming, and integer programming. So genetic algorithm is an example, is a population based meta-heuristic. All right, is an example of population based meta-heuristic. The short form of population based meta-heuristic is written as P-Metaheuristic. And this is a high level template of how a P-Metaheuristic works. You see, in S-Metaheuristic is single solution based meta-heuristic. We had one solution. So I'm writing a solution in a list form because we talked about representation in our previous class. I hope you remember. If you don't remember, you can just stop me. I'll just revise it. So this is one solution. And what we try to do in single solution based meta-heuristic is we try to improve this solution using the idea of neighborhoods. Okay, so we try to move to a neighbor where the objective function is better. So if it is a minimization problem, it is lower, and if it is a maximization problem, it is higher. Okay, so we try to move to a better neighbor, and you see we are always focusing on that single solution. We are always stuck with that solution, and we try to improve that solution. In population based meta heuristic, the idea is a little bit different. We will not work with just one solution. We will create a population of solutions. So the size of the population can be anything. You have to determine the size of the population. So suppose, for example, the size of the population is 30. So there are 30 individuals in that population. That is, there are 30 different solutions in that population. So this is one solution. Similarly, we'll have other 29 solutions, and we'll call them individuals, and together we will call them as population. Okay, so what we'll do is we will initialize the population. That is, we'll try to get these 30 individuals. Either you can use some other heuristic or meta heuristic, or you can just randomly generate these individuals. The practice in this population based meta heuristic is to try to generate randomly generate the initial population. Okay, it is known as initial population. So we randomly generate 30 solutions. Okay, so if this population size is 30, we'll randomly generate 30 solutions and we'll label this as the initial population. And in this S meta heuristic, what we tried to do is we had one solution and we tried to improve that solution. Over here, what we'll try to do is in this population, we will do some modifications to the individuals and we'll try to move to better solutions. Okay, so this is the idea. So initially we were only having one solution and we're improving that solution iteration by iteration. Over here we will have a population of individuals and we will try to improve the best solutions in that population at each iteration. So over here this iteration, when I'm saying, it is known as generation. Okay, so this 30 individuals is the first generation and in the next generation there will be some so it is actually very similar to how evolution works. Okay, so if you go back and if you know about Darwin's theory of evolution, you might have known that he has proposed a theory that the evolution occurs and the best individual in the population survives, and then the fittest of the populations, the individuals in the population survive and the population becomes better and better. So that is the idea. We'll start with one population and we'll call that generation 1 or generation 0. You can start with 1 or 0. We'll move to generation 2. So same 30 individuals can be there. You can increase the population size or you can remain at the same population size. So we are saying the initial population size is 30 and at each generation we'll stick to that population size only 30. We'll move to generation after generation. Okay, and there will be some terminating criteria at generation n where you will have another 30 individuals in that generation, but these individuals will have good solutions. And you see, at each iteration the individuals are actually becoming better in some way. And what is happening is, so if I just draw one, so what is happening is you might have multiple local optima in a problem, right? So if it is a minimization problem, this graph is for a minimization problem, you might have multiple local minimas, right? And what will happen is, since you have a population, those populations will come close to this local minima. And what you will do, you will pick the best individual in that population. So for this example, you see, this is the best individual. If these are the populations you have, so you see this will be the best individual in the population and you will say this is the best solution. So at last generation, something like this will occur. So initially when you start, it will be randomly distributed over this space. It will be randomly distributed over this space, right? Something like this. And generation after generation, it will try to move towards the local optima, and they will be concentrated in the multiple local optimas you have. And the best individual in the population will say that this is the solution, approximate solution to the problem. Okay, so we'll start with generation 1 and we'll move to generation n. So you see what are we doing in this algorithm? We will see. So we start with the initial population P naught and we'll say the generation is 0. So over here we're starting with 0th generation. In this example, I had started with generation 1. Doesn't matter, it is just a label. So we start with generation 0. While a stopping criteria is not met. So there can be multiple stopping criteria. You can say I will just go for 1000 generations, or you can say that I'll run this algorithm for 1 hour or something like that. Some stopping criteria has to be there. Okay, what you will do is from this generation, so what you will see at generation 0, so currently t is equals to 0, we will say generate p dashed t. P dashed t is a new generation. And what you will do is you have p dashed t, you combine pt and p dashed t. So you had pt is a one generation and you had p dashed t as another generation. You combine all the individuals in that generation and you pick So suppose 30 is the population size. When you combine, it may become 60. 30 for P0 and 30 for P0 dashed. So you will have 60 individuals. From that 60 individuals, you again select 30 of them because you want to stick to 30 individuals at each generation. So you will have PT plus 1. So it will be P1. You will have generation P1, population P1. And what you do, you increment T. So this is how we are doing. We are going from one generation to the other. So you see this words generate, select, these are very big words. We don't know what it means right now. We're just saying we are at population 0, generation 0. So we'll just start with 0, population 0, and we had 30 individuals. We generate 30 more individuals. Okay, somehow we will talk about how we are doing it. Somehow we generate 30 more individuals. So we'll have in total 60 individuals. From this 60 individuals, we pick 30 individuals for the next generation, which is generation 1. Again, you generate another 30 individuals. You combine these two, 30 plus 30, it will become 60, and then pick or select 30 best individuals. So you will have G2, generation 2, and you go on and on and on until you have generation N. Right? Okay, so this is the idea. Now we'll talk about what do we mean by this generate and what do we mean by this select from this population. Is it clear? So in some sense, this generation is actually reproduction. So from this 30 individuals, these are parents of the new generation. Okay, so when we are generating 30 more individuals, the parents are actually recombining their genetic material. So what do I mean when I say genetic material? You see, we have talked about representation. So each representation is actually labeled as chromosome. Okay, so what is it? It is, so suppose for traveling salesman problem, it will be just a list of ordered cities, right? So it is one chromosome of an individual. So for example, individual 1, I1, can have a chromosome of A, C, B, D, F, E. So this is a chromosome of this individual where we have 6 cities. Another individual can have a chromosome of E, D, A, B, C, F. This is another chromosome of this individual. So we identify an individual by its chromosome. And in the single solution based metaheuristic, we were labeling it as representation. Okay, so this is the representation of the chromosome of an individual. We will have, if the population size is 30, so we'll have 30 individuals and each will have a chromosome, right? And when we say generate some more individuals, we will try to recombine this. Um, we will try to recombine this uh, genetic material. So this chromosome is actually a genetic material. So we'll try to recombine this genetic material with uh, two parents. So we'll pick, suppose we are picking I2 and I7. So we are picking two parents and we can generate one child. So we can say child 1, or you can generate two childs, child 2. It's up to you. How are you recombining? There can be multiple ways to recombine. So if you remember, when we were talking about neighborhoods, there were different ways to create neighborhood. Similarly, there are different ways to do reproduction. Over here, we are talking about reproduction. We'll see how we do reproduction. We are just talking about the higher level stuff. So we pick some parents. So what will we do? So here we have 30 individuals. So suppose we are picking 10 parents and we are pairing them up. So we will have 5 pairs of parents, right? So we'll have 5 pairs of parents, and suppose this 5 pair of parents produces 10 offsprings, right? So we had 30 individuals in a generation, we produced 10 offsprings, not 30 for this example. So in total we have 40 individuals when this offsprings and this earlier generation combined. Now what will we do? From this 40 offsprings, we will select for the next generation. So suppose this was generation 1, we will select 30 individuals to become generation 2. Okay, so this is how it is produced. Proceeding, we have a generation, we do reproduction to create more individuals, we combine the new individuals created and the earlier population, and then we pick 30 of them, if the 30 is the population size, to become the new generation. Again, from this new generation, we'll pick some of them to become the parents. Those parents will recombine or reproduce to give offsprings. We will combine the offsprings with the population, and then we will pick some of them. If 30 is the population size, then we'll pick 30 of them to become the next generation. Okay, so this is the idea. Any questions? We will talk about how are we doing reproduction, how are we selecting parents, how are we selecting offsprings. Those we will talk about. Any questions? Okay, so let's see what I have written in the slides and then we'll talk about one step at a time. So this is an inspired by nature. So you see genetic algorithm was mainly developed around, so it started around 1970s, 75s, but the major development of genetic algorithm took around 1990s. So it is relatively new algorithms and it is inspired by nature. Okay, so it mimics the process of evolution to solve optimization problems, operates on a population of candidate solutions called chromosomes, iteratively improves solution using genetic operators. So when we were talking about recombination of chromosomes, we were saying those are genetic operations performed. Okay, so what is selection? uh, okay, so before going into these, it's better that I give you more idea, then this terminology will make sense. Okay, all right, so what we'll do is we will see one example problem and then we will talk about these aspects: selection, crossover, mutation. What are these? Okay, so suppose we were talking about a traveling salesman problem. Okay, a traveling salesman problem, or maybe a knapsack problem will be better. So can anybody tell me what is a knapsack problem? We talked about this in the last class, knapsack problem. What is a knapsack problem? A knapsack problem, I'll discuss it then. You see, we will have a container which has a capacity and you have some objects. So object 1, 2, 3, n. Okay, we have some objects. Each object has a weight w1, w2, w3, wn, and each object has a reward r1, r2, r3, rn, right? And this bag has a capacity of C. So what is the problem? You have to pick objects such that you do not exceed the capacity of the bag. Moreover, you have to maximize the reward you are getting when you are picking these objects. Okay, so you can pick from these n objects how many number of objects you can. You have to just ensure that the capacity of the bag is not exceeded and the reward, your total reward you are getting is maximized. This is the problem. Okay, so we talked about the representation of an abstract problem. You can have a list of n elements and each element can either be 0 or 1. Okay, it can either be 0 or 1. So when I say 1, it means we are picking that object, and when I say 0, it means we are not picking that object. Okay, so it means over here object 1 is not picked, object 2 is picked, object 3 is not picked, object 4 is picked, object 5 is picked, object 6 is picked, object 7 is not picked. And since this representation have 7 elements, we are talking about an abstract problem with 7 objects. Is that all right? Please speak up. If you don't speak up, then I'll not understand whether you are understanding the problem or not. Okay, so this is how, this is what a knapsack problem is. So what we'll do is we will say there are n number of elements. So we'll just increase the number of elements. It can be 30, 40, 100, whatever you can think of. Now what I will do is I will tell you the parameters of genetic algorithm. So first you have to think about what will be the population size. Okay, so we'll take some examples. Population size. So suppose we are saying we will have a population size of 10. So we'll have a starting population of size 10. So what will we do? We will randomly generate 10 individuals. How will we randomly generate? We'll say this can take either 0 or 1. This can take either 0 or 1. So one individual we can just randomly generate. Okay. So we have 10 individuals in that population. So this is generation 0 with 10 individuals. All right. Now the first was population size. We have fixed the population size and we have 10 individuals in that population. The second aspect of genetic algorithm is parent selection. So since this population size is very low, we can have higher population size. The higher the population size, it is better to have, but it increases the space complexity of the problem because you have to keep the data of all the individuals. But for example, we are saying, just to make a point, I'm saying there are 100 individuals in this population. Now, to do reproduction, you just cannot pick all the 100 parents. You have to take a subset of the population. So suppose we are saying we'll pick 30 individuals from this generation to become the parent of the next generation. So what do you want? We want to pick good individuals to become parents of the next generation. So that is how in evolution works, right? Better individuals have a higher chance to go into the traits of better individuals have a higher chance to go to the next generation. So Darwin's evolutionary theory, the theory of evolution, has been proposed like this: survival of the fittest. So whoever is good individual in this population, that trait is retained in the next generation. So we will select 30 individuals from this population. There can be multiple ways to select parents. So what you can do is you can pick the best among these 100. So you can pick best 30. That is known as elitist selection. ELITIST, elitist selection. It means the good individuals from that population. Okay. You can pick the best 30 individuals from this population. You can have other criterias as well. So what you can do is you can give rank. So each individual, whatever its objective function is, higher the objective function, more is the those are good individuals. So you can have some stochastic criteria. So higher the objective function, higher is the probability of that individual to become the parent of next generation. Okay. So there can be multiple criteria or multiple ways you can select parents. We'll not talk about the ways of selecting parents, but you should have an idea. Okay. So there can be multiple ways of selecting parents. For this problem, we can say that from 100 individuals, we'll pick the best 30 individuals to become the parents of the next generation. Okay. So we have talked about population size. We have talked about parent selection, and we have also talked about one AL, right? We have also talked about initial population. So how are we generating initial population? In this example, we are randomly generating 100 individuals. Okay. So we have done parent selection. Now what will we do is reproduction. It's not 2, it's 3. Reproduction. So reproduction in genetic algorithm has two parts. So 3A, it is known as crossover. And the third next is mutation. So what is crossover? Crossover is, so each individual has a chromosome, right? So crossover is the mixing of this chromosome. So you can take half. So suppose this is individual 1, right? I1, and this is individual 2. So what you can do is you can split this chromosome of an individual in halves. And what you can do is you can say this half and this half will become offspring 1. Okay, so it will be this and this, and this half and this half will become offspring 2. So this is coming from, okay, sorry, this is coming from here and this is coming from here. Okay. And for this individual, if I say this is the chromosome, so this part is coming from here and this part is coming from here. So this is one crossover operator. There can be different ways of doing crossover. Okay. So this is the idea of crossover. There can be multiple ways of doing crossover. Over here, I have talked about single point crossover. You are just splitting the chromosome in one point and then mixing it. There can be multi-point crossover. There can be other ways also of doing crossovers. Okay, we are just giving over upper se idea we are giving. Okay, so this is how crossover is done. We are mixing individuals for parents chromosome to become new chromosome of children. Okay, now once we have a children chromosome, so we will take one example. So suppose we are talking about this knapsack problem. So suppose this was the knapsack individual one. Okay, so this is having seven elements. This was individual one, and this is individuals. So this is individual two. Now what will we do? We'll randomly pick one crossover point. So suppose we have picked the crossover point like this. So this is the crossover point. Now we can generate two individuals. We will take this part, and this part will create offspring one. So offspring one will have this part. It will be 0 1 0 1 1, and this part which is 1 1. Okay, and for offspring 2 we will take this part and this part, so it will be 0 0 0 1 1 1 0. Okay, so we have created from two parents, we have created two offsprings doing crossover. Now what is mutation? Mutation is random change in an element of the chromosome. So this, what it does is it can pick any random elements in the chromosome. So for offspring 1 it is picking suppose this one, and it is randomly changing its value. So from 0 it can change to 1. So offspring 1 dashed will become 0 1 0 1 0 1 1. So one we are doing crossover and the other we are doing mutation. So if you remember in the last class we were talking about intensification and diversification. So do you remember what is intensification and diversification? So intensification was we are sticking to a solution and then we are trying to search very close to that solution, and diversification is going into other areas. So this crossover is actually an intensification operator. How, we will talk about that. And mutation is actually a diversification operator. So you see, when we are doing crossover, we are picking best parents. So the properties of the parents, of two parents which are good parents, are mixed up, getting mixed. So it may happen that the good property of parent 1 and good property of parent 2 combines together and gives me a good individual offspring 1, right? So this is doing intensification. Crossover is actually picking properties of parents and combining it to become one parent. Mutation is actually doing the diversification. It is randomly picking some elements and randomly changing it. So it may happen that offspring 1
Acha,
was a good.
I have
Yes.
one doubt just. This crossover, is it not diversification? Because if we consider two solutions from two different locations and they are nearby their own means local optimal solution. Now, whenever we shall do the crossover, it may jump to another part. Rather, whenever mutation we shall be doing, it is already the crossover children has been generated. Then around that region we are doing the mutation, means it is a new region. So in that new generation, wherever that new child has been generated, there is it not intensification?
So over here we are talking just about knapsack problem. So in this kind of problem, you may think that crossover is actually doing. Um, I'll tell you. So crossover is actually doing diversification, and mutation is actually doing intensification. But if you think about it, when we are doing crossover, you see big regions of one parent are staying constant, right? So it may happen that that region of that parent is a good region and the other region of that parent, so suppose this is parent 1, for this parent this region was a good region and this region was a bad region, right? So what are we doing? From this parent we are picking the good region and we are keeping that good region in the offspring. offsprings. We are not changing that good region. We are splitting that bad region and we are bringing another region from another good parent to mix with the good region of parent one. So in a way, we are trying to pick properties, good properties from parents and bringing them together. So we are preserving good properties of parents. That is why it is intensification. So you see, when we talked about intensification in single solution, we were just talking about in that region. But intensification has a higher level definition as well. Intensification means we are some traits of that region. So suppose, so for this knapsack problem, it might happen that 1, 2, and 3 are good objects to pick up, but not the other. So if we keep those constant and change the other, then we are in a way doing intensification. We are fixing these 3 objects. We are saying that these 3 objects will always be there in my bag. I will change other objects. So actually it is doing intensification. If it might be problem specific, you can think about, but crossover is actually intensification. We are preserving properties of parents. But mutation, what it is doing, it's randomly changing. So it is saying I will not bother about. So you see, for knapsack problem it might not make sense. But if you go for traveling salesman problem, then it will be better explained. So you see, when we have a traveling salesman problem, so suppose this is the cities we have, and this is the tour we currently have, right? Okay, so this is the tour we have. Sorry. Okay, so we have, this is one node, this is another node, this is another node, this is another node. I'll show you how this crossover is preserving that region. So you see, this is good region, this is good region, right? And this is a bad region, right? So this is good region, this is good region, and this is a bad region. Are you able to see good region and bad region? So suppose this parent one is combined with another parent which had this kind of regions, right? So this parent has this region, suppose. Okay, now you see, this parent has this as the bad region, this is the bad region, and this as the good region, right? For traveling salesman problem. So the upper part is a bad region, the lower part is a good region. And if you recombine these parents, and suppose this was the partition of recombination, this area. So this good region and this good region will create a good children. And that is why we are saying that crossover is a intensification operator. Is that all right? Okay. And mutation is a diversification operator. It just randomly shifts. So over here you see the adjacency is more important. So in knapsack problem, the adjacency was not important because adjacency just means object 1 and object 2. But in traveling salesman problem, the adjacency means something. When city B is close to city F, it means we are going from city B to city F. And if we are preserving that adjacency, then we are preserving good areas. All right. So in some of the problems, crossover operators, so we have to think about for which problem which kind of crossovers are good. So over here we have just talked about single point crossover. There are other kinds of crossovers as well. Okay, so come back here, we have an idea. So we are giving an idea of genetic algorithm. So first we talked about population size. Second, we talked about initial population. How are we generating initial population? We are generating it randomly. Then we are doing parent selection. Thereafter, we are doing reproduction. So you see, when we have done parent selection and then reproduction. So suppose after reproduction, so we had selected 30 parents and we generated 30 offsprings because we two parents are creating two offspring. So suppose we have 30 number of offsprings. So in total, total individuals we'll have 100 plus 30, which is 130. Out of this 130, you have to select individuals for the next generation. So this is another kind of selection. This is another kind of selection, which is not parent selection. It is not parent selection. It is selection for the next generation. Okay, so this is also known as selection. Just a minute, what I have written over here. Yes, selection. Selection. So what this selection is, among these 130 individuals, we have to pick 100 individuals to go to the next generation. So generation 1. So we started with generation 0. We have to go to generation 1. So over here also what you can do is you can pick the best 100 individuals from this generation. So you can just take best 100. But this is not a good idea to do. So when you pick best 100, what are you doing is you may go to earlier convergence. So it means what are we doing? We're just going for the best, just going for the best. But sometimes randomness helps to explore other areas. So what is generally done is we pick, suppose 80% best solutions. So from this 130, we will pick 80 of those as best and 20 of those we will pick randomly from this, right? So we'll just pick 80 best and 20 we will pick randomly because we want some diversity in the population. We don't want to just concentrate the population in one area, not just the best ones. We want some of the individuals with lower objective function as well, because if that is selected to do parent selection, it might bring some diversity in the chromosomes. So those are intricate details, but I'm telling you because we are here. So we have done selection, then we'll just repeat. So when we have another generation, we will go back. We have generation, we will do parent selection, then we'll do reproduction, then again we will do selection for the next generation. So this algorithm which is written over here, it is the same thing which I am talking about. You see, we are starting with a population. Until the stopping criteria is met, there can be some stopping criterias. For example, if the objective function from one generation to the next generation is not changing. So suppose you are at generation 100 and for 101, 102, 103, 104 and so on and so forth, suppose for 120. So from 100 to 120, the objective function did not change. The best objective function, the best individual in the population did not change. Then we can safely terminate the genetic algorithm, saying that we suppose that we have converged to a solution. That can be one stopping criteria. There can be multiple stopping criteria. Okay. So we generate new individuals. So this generate is actually a compound term. In this generate, we are selecting parents and doing reproduction. Okay. So when we are saying generate, we are actually selecting parents and then doing reproduction. And next we are selecting the next population and then we are repeating. So this is the simple idea of population based meta-heuristic. And mind you, we have just talked about one population based meta-heuristic, that is genetic algorithm. There are multiple different population based meta-heuristic. For example, ant colony optimization, bee hive, ant colony optimization, artificial bee, I don't remember all the names, but it was artificial. One is artificial immune system, another is particle swarm optimization, and many more algorithms are there. But the basic idea remains the same. We will have one population, we will try to generate some new individuals, then we will select the new population and we'll just reiterate. So all the algorithms which I was naming has the same basic structure. Is that all right? Okay. Now, one thing I have not talked about since the last class also and this class as well, about constraints. You see, when we are doing recombination, so over here when we are doing, so you can say crossover or recombination, doesn't matter. When we are doing this crossover, it might happen. So for example, in this knapsack problem, you might create an individual which does not satisfy the capacity, right? You might have an individual, suppose all ones. So you can have a individual as all ones, right? 1 1 1 1 1, and that individual will not satisfy the capacity. what will you do with that individual? So there are multiple ways to handle constraints. This is a constraint, right? That you have to satisfy the capacity of the bag. So there are multiple ways to handle constraints in both in single solution based meta heuristic and population based meta heuristic. And I'll just give you some idea. I have not taken here because those are not necessary in this course. If you take a course on optimization, then it becomes necessary. But still, I'm telling you some of the ways of handling constraints. One thing you can do is you can just reject that individual. You can just say whenever the constraint is not met, we will not pick that individual. We'll just reject it. And for single solution meta heuristic, if you go to a neighbor which is not satisfying the constraint, you will just reject that neighbor. You will say we will not um, make that will not think it as a neighbor. We'll just reject that neighbor. Okay. So this is known as rejection strategy to handle constraints. There are other ways also. I'll not go into more ways, but yeah. So there are ways to handle constraints. If you are interested, you can just talk to me after the class or maybe afterwards. Okay. Any doubt in genetic algorithm?
No, it's fine.
All right. So what are the key features? Okay, before that, we were here. So we are saying selection. So what is selection? Retaining the fittest individual based on their objective function. It is not true. We not always pick the best individuals. There are other ways for selection as well. But I have written over here because for beginners, this is what we do. We just tell them to pick the best individuals. Crossover is combining parts of two parent solution to create new offsprings. Mutation introduce small random changes to maintain diversity in the population. You just don't want your population to converge to one area of your search. You want it to diversify to other areas as well. So when you mutate, some of the individuals just randomly go to other areas of the population. And one thing, so this crossover and mutation, there are rates. So for crossover, so you can just say, so when you have suppose 30 parents, you can just say we will do for each pair we will do crossover. So the rate is 1. For mutation, you can just say we will do mutation 5% of the time. So generally we prefer mutation rate as very low. We don't give a high mutation rate because it may become erratic. So mutation rates are very low as compared to crossover rates. Okay, so mutation probabilities are very not significantly low, but it is lower. So suppose it can be 5% or 2%, something like that, just to encourage diversity. Okay, so provides a balance between exploration and exploitation. So you can just, when I have written exploration, mutation and crossover and exploration selection, so you can just think it is problem dependent. Some crossover operators are actually exploitation. Okay. So some crossover operators can become exploitation. You are keeping regions of good individuals. The selection also has exploitation. When, so you see, if you pick good individuals to become parents, you are actually doing exploitation. You are saying, I will remain in this area of the search. Why? Because you are picking good individuals to become parents. So this crossover generally is in exploitation, but over here I have written exploration, but generally crossover is in the exploitation region. Applicable to complex and modular multimodal. So what is multimodal? I'll tell you. Applicable to complex multimodal search spaces where exact methods are computationally expensive. What is multimodal? So whenever you have a problem which has multiple local optima or local optima, so if it is a minima, multiple local minima, and if it is a maxima, then multiple local maxima, then that problem is known as multimodal. So it has multiple minimas or multiple maximas. Then that problem is known as multimodal. And what happens is if your search problem is multimodal, doing a single solution search is not good. What you will do is you will come to an local optima and you will say this is a my local optima. So you have to go for maybe taboo search or simulated annealing, some way to escape that local optima. You just cannot do local search. You'll just get stuck in local optima. Okay. So if you have multiple minimas, local minimas, then you should go for population based meta heuristic. Now you might ask me question, how will we know that if a problem has multiple local minima? So that is a difficult problem question to answer. Okay, so that is problem dependent as well as instance dependent. So we were talking about last class when we were saying some neighborhoods are better than the other. So for traveling salesman problem, we talked about that two opt neighborhood gives very low number of local minimas. It has a very good big global minima. So these are problem structures that has been studied by researchers. We currently know that if we have a traveling salesman problem, going for two opt will give me a good local minima. Okay, so these are very difficult problems to answer. Okay, so key features: population based search operates on multiple solutions simultaneously. Scalability, can adapt to different complex problem complexities. Flexibility, work with binary, real valued and permutation based representation. So when we talked about knapsack problem, it was a binary problem, right? So the representation was binary. When we are talking about traveling salesman problem, the representation was permutation based. It can be real valued also, but generally we use genetic algorithm for permutation based or binary. For real valued, there are other better algorithms like particle swarm optimization. It is very good for real valued problems, and colony optimization is also very good for real valued problems. One thing which I want to emphasize on is this permutation based. So let me take an example of traveling salesman problem. So if an individual one, so suppose we say parent one. So suppose parent one is A, B, C, D, E, F, and parent two is B, A, C, F, E, D. Okay, so this is two chromosome of two individuals. Now what will we do? Suppose we are doing 1 point crossover. So what will we do? We will split it. So suppose this is the crossover point and we will generate offsprings. So for offspring 1, we will have A, B, C, F, E, D. And for offspring, just a minute, and just what I will do is I will change this offspring. So suppose this offspring is actually DBA. So suppose offspring B, parent B is DBC FEA. Now what will offspring 1 become? Offspring 1 become ABCFEA, offspring 1. And offspring 2 will become, so this is offspring 1 and offspring 2 will be this, which is DBCDFE. Do you notice something here? Do you notice something here? You see?
Offspring 2 is leaving A.
Yes, so over here it doesn't have A and over here it doesn't have D, right? So these are some technicalities you have to make sure when you're doing crossovers. In permutation based representation, when you have a permutation and you're doing crossover, then that permutation may not reflect in the offsprings. So there are multiple ways to handle this. One way is to do restoration.
So
Yes.
this can be considered as constant, correct? Means constant was that in every offspring, all the A, B, C, D, E, F should be there. So this
Right.
can be rejected based on the constant violation.
So if you reject this kind of offsprings, you will actually reject a lot of offsprings. Just imagine you are doing crossover of this kind, and if you just think about it, most of the offsprings will not satisfy this constraint. Most of the
Yeah,
offsprings.
that yes, that is true.
Just cannot reject all the offsprings. That is a very bad practice. So what you can do is one way to handle this is to repair. So repair the solution, offspring repair strategy. This is also a constraint handling strategy. Okay. So there can be multiple ways to repair. So what you can do is whenever the A is repeated, you will just make it D, or there can be multiple ways. We cannot go into each and every way. I'll just tell you what are the problems you may encounter. So over here, one way of doing repair is to just remove the second occurrence of the element to the element which is not there, or there can be other ways as well. Which way will work better? It depends upon your problem, and you have to have some experience of that problem. Otherwise, some repair strategy are not good. So suppose when I'm saying whenever you encounter a repeat, so A, B, C, F, E, you are encountering a repeat. Now I'm saying just enter D over here. Now suppose there was not only D, there were multiple. So you had D, F, E. There are three elements there. Which one to enter? Whether to enter D or to enter G or to enter E or something like that, right? So you have to devise repair strategy such that it works for you. So this is not very, so permutation based representation has this difficulty when doing crossover. Okay. There can be other ways of doing crossover. So over here we are talking about 1-point crossover. So I'll give you one more example. 1-point crossover. Another example of crossover for this traveling salesman problem is what you do is whenever you are doing crossover, you select the crossover point for one parent. Okay. So you select crossover point for one parent. So what I'm doing is I'm selecting crossover point for parent 1. So my offspring 1 will become this region of parent 1. I'll say A, B, C is my first part of offspring 1 from parent 1. Now what I can do is I can move to parent 2 from the start, and I will remove these elements. I will remove B I have taken, C I have taken, and A I have taken. I am removing these three elements from parent 2, and I will retain the order. So we can have D, F, E. So this is offspring 1. Offspring 2, what I can do is I can reserve this. So I'll say D, F, E. And what I will do again, so for offspring, so for parent B, I have D, B, C, F, E, A. Again, I will strike out these three elements. I'll strike out D, F, and E, and I will retain the order. So we'll have B, C, A, something like that. So this is a strategy where you will not encounter the problem which we are having in 1-point crossover. This is another way of doing crossover where we are trying to handle that issue we were having. So you see over here we'll not have repeat elements, right? Is that all right? Okay. So you see over here we can create actually 4 children, 4 offsprings, offspring 3 and offspring 4. How can we create 2 more offsprings? Instead of picking a point in parent 1, you pick a point in parent 2. So suppose we picked this point, and we will do the same thing. We will keep D, B, C, F in offspring 3 and 2 from offspring parent 1, and E and A, the 2 elements, and then 4 elements from here. So you, in this kind of crossover, you can create 4 offsprings. From 2 parents, we are able to create 4 offsprings, right? So there are multiple ways to do crossover. So that is the whole idea I'm trying to bring over here. Is that all right? Okay, so I assume it is all right. Right, so I have given one example of traveling salesman problem, initialization, evaluation. So when we are saying evaluation, it means what is the objective function value of that individual. So it will tell you how good is that individual. Okay, so when I say evaluation, it measures, so this is one terminology used, fitness. So how good is that individual? What is the fitness of that individual? Okay, selection, crossover, mutation. Right, so over here we are initializing one population of suppose 3 routes. Then what are we doing? We're calculating the fitness. So over here, this fitness term means whenever it is higher, it is good. Okay, so for a maximization problem, the objective function will become your fitness. Whatever the objective function value, that is the fitness of that individual. But for a minimization problem, you have to inverse it, or there are other ways also. So over here I am just inversing it. So 1 by distance, higher is the distance, higher is the fitness, higher is the distance, lower is the fitness. So suppose the distance is 200 units, then the fitness becomes 0.005. If the distance is 210, then the fitness becomes accordingly. So over here, fitness means higher the fitness, good is the individual. So that relation you have to keep in mind. Okay. Now we are doing selection. So I talked about uh, elitist based selection, but over here I am given another example of selection: roulette wheel selection and tournament selection. So what are these? So roulette wheel selection is coming from gambling. So you will have a wheel and you have parents, right? Individuals, right? So suppose you have 100 individuals. What you will do is you will divide this wheel into 100 regions. But the area of this region will be proportional to its fitness. So higher is the fitness of that individual, higher will be the area in the wheel, right? So 100 regions will be there, but higher fitness individual will have a higher region. Now what you do is you have a arrow and you rotate the wheel. So wherever the arrow lands, that becomes selected parent for doing reproduction. Again, you rotate the wheel. Wherever the arrow lands, that became the selected parent for doing reproduction. So this is roulette wheel selection. Is that all right? Is that all right? Okay. Tournament selection. So this is similar to selecting fittest individuals. What we do is we have 100 individuals in the population. We will do tournament, but not for all 100. We will say the tournament size is 30. So we will pick, that is also picking some individual. Okay. So we'll pick 30 individuals. We can do it randomly pick. Suppose we are doing randomly 30 individuals. In this randomly selected 30 individuals, we will do tournament. That is, whichever is the highest fitness individual, we will say that is the winner and he is selected as the parent. Now from the 99 remaining, again we'll randomly pick 30, and from that 30, whichever is the highest rank individual or highest fitness individual, that is selected for parent 2. Again from the 98 remaining, we will randomly pick 30 and then we'll do the tournament. That is, whichever is the highest fitness is selected for becoming parent, something like that. So randomly picking a subset and then choosing the fittest from it. It is a selection strategy. Okay. Is that all right? Right. So crossover. So over here, what are we doing? We are doing that crossover which we talked about. So example of crossover, this is parent 1 and this is parent 2. Okay. Okay. So from parent 1, we picked this is the crossover point. So we pick A, B, C, D. And from this second parent, we pick the unique elements, right? That is what we were talking about when we were talking about crossover in permutation based. So we will remove A, C, D, B, and then we have F, E. So we'll have F, E, and then the offspring will become A, B, C, D, F, E. Second offspring, sorry. Second offspring is also selected in a similar way. Okay, so the new offsprings are selected to become the next individual. So mutation. So over here, so when we were talking about knapsack problem, the mutation was just to flip that bit. So if it is 1, it will become 0. And if it is 0, then it will become 1. So that is one kind of mutation, which we do in binary selection, binary representation. In permutation based representation, there can be multiple ways to do selection. Over here, we can just do swap. So for this, we can swap C and F. So that is one way to do mutation. Another mutation is insertion. So the way we talked about so if you remember, we are talking about how to create neighborhoods, right? Neighborhood. So when we're talking about how to create neighborhoods, we had swap neighborhood. The second was insertion neighborhood. The third was to-opt neighborhood, if you remember. So those neighborhoods will become mutation over here. For that individual, we will change something in the representation. So we will swap city C and city F, or we will just pick this E and we will insert it over here. That is insertion. These kind of neighborhoods. So that idea of neighborhood will become mutation in this. Is that all right? Is that all right? Okay. So we have talked about mutation, and then yeah, we will just iterate repeatedly and then pick the, so whatever you say, you can just go for number of generations. You say I'll go for 100 generations, or multiple stopping criterias can be there. So that is it for genetic algorithm. Any questions on genetic algorithm? So we will take 5 minutes break and then we'll move on to linear programming and integer programming. All right. Okay. Okay. So far we have covered approximate algorithms, right? So we were talking about heuristics. We just saw one, that was greedy heuristic. I hope you remember about greedy heuristic. Then we saw meta heuristics. We saw examples of single solution meta heuristic like local search and simulated annealing. And we saw one example of population based meta heuristic, that is genetic algorithm. Now we are moving on to exact methods. So first we will see linear programming, and it is a very fundamental uh, mathematical programming approach to solve problems with some properties. So for linear programming, so the name is there, linear. So your objective function and constraints has to be linear, and the decision variables, we will see what decision variables are. The decision variables has to be real valued. Okay, so these are the some properties needed for your problem to become a linear programming problem. So we will see one example of Carpenter problem. So the problem goes like this. There is a carpenter who makes chairs and tables. So suppose X represents the number of tables he produces and Y represents the number of chairs he produces, right? Each table is sold for 7 units and each chair is sold for 4 units. So the total revenue he will have by selling X number of tables and Y number of chairs will be 7X plus 4Y. So this is the revenue he will have. If he produces X number of tables, the revenue from table will be 7X, because 7 is the unit sales price of that table. And if he produces Y number of chairs, he will have a revenue of 4Y, because 4 is the price of the chair. So the total revenue is 7X plus 4Y. There are some constraints. So the total unit of timber or wood he has is 40 units, and table requires 5 units of timber and chair requires 2 units of timber. So the 5x is the total units of timber required for tables, and 2y is the total unit of timber required for chairs, right? Each unit requires 2 units. We are producing y number of chairs, so we'll have 2y. If you add these two ups, 5x plus 2y, so 5 units of timber per table, so 5x means total timber for table, 2y means total timber for chair, and this is the total timber used. It has to be less than 40 units, because 40 is the unit of timber he has. Okay, so this is the timber constraints. Another is the labor constraint. So each unit of table requires 9 hours of labor, and each unit of chair requires 6 hours of labor. So 9x plus 6y is the total number of hours he requires labor. So total number of labor hours he requires, and he only has 90 units of labor hours. So these are the two constraints he have, and obviously the non-negativity constraint, that x and y cannot be negative. So it has to be greater than equals to 0. So when we write the problem like this is known as the objective function. These two are known as the constraints. Actually, these three are known as the constraints. Okay. So when we write like this, and this is the decision variables, these are the decision variables. When we write a problem like this is actually a mathematical formulation of the Carpenter's problem. And this mathematical formulation, if you observe, is linear. The objective function is linear. The constraints are also linear. And therefore, this is a linear programming problem. If you solve this problem, and so I forgot to mention that Carpenter wants to maximize the revenue. Okay, so the objective he has is to maximize the revenue he is getting by selling the tables and chairs. So the question is, what is the unit of table and chairs he has to produce such that the objective That is, the revenue is maximized. So that is that problem. And if you formulate that problem, you will get this mathematical model, and you observe that this is a linear model, and therefore this mathematical model is actually a linear programming model. This programming has nothing to do with the programming which we do in computers, that coding. Okay. Is that all right? Okay. If you solve this problem, if you maximize this objective function such that these constraints are satisfied, then you will have one solution, which is the optimal solution of this problem. Okay. Now, if you observe, if these constraints are not there, these two constraints are not there, then you can produce infinite number of chairs and infinite number of tables. And the solution will actually be infinity comma infinity, and the objective function will become infinity. Since you have constraints on labor and time, timber, you will not be able to produce infinite amount of both the goods, the tables and chairs. Therefore, these constraints are actually restricting the values this decision variable takes. Okay. And there are ways to solve this problem. And if you have a problem, and if you have formulated it as a linear programming problem, then there are standard algorithms, or there are standard solvers as well, which can solve linear programming problems very easily. Okay. So all constraints and objective function are linear functions, making it this a linear programming problem. Any questions? We will see one method to solve linear programming problem when you have two variables. Okay. For two variables, how can you solve this problem? And for higher number of variables, if you have n number of variables, say 1000 variables and 1000 constraints and so on and so forth, how do we solve that problem? So we'll talk about the algorithm. We will just see what are the algorithms. We'll not go into details of those algorithms. Okay. So the first method which we'll see is graphical method. So over here, this graphical method. So since we are using a two-dimensional graph, it can only be solved if you have two variables. Okay. You will not be able to solve linear programming problem using graphical method if you have more than two number of variables. You can go for three number of variables, but you have to imagine it in 3 dimensions. You can do that. You can do that. But going beyond 3 dimension is not possible using this method. Okay. So we'll see one dummy problem. So this is a dummy problem. The objective is to maximize 2x minus y, and the constraints are x is less than equals to 3, x minus y is less than equals to 1, x minus 2y is greater than equals to 0, and the non-negativity restrictions is x and y has to be greater than equals to 0. We have to solve this problem using graphical method. So before I show you the graph, let us draw the graph together. You can help me as well. Okay. So first I'll draw the first quadrant. You see, both x and y are greater than equals to 0. So we will always be in the first quadrant. Okay. So we'll always be in the first quadrant. So do I have lines? Okay. So we will always be in the first quadrant. Now, if you observe this constraint, x is less than equals to 3 is also a vertical line. Okay. So it will be like this. Right. Okay. Sorry. It will be like this, where this is x is equals to 3. So this is x-axis. This is y-axis. This is origin. Okay. And these are the regions till now. So this and this. How do we know? So you see, when I say x is greater than equals to 0, so this is the x-axis, and this is the region where x is greater than equals to 0. Therefore, I am drawing this arrow. This side is feasible according to that constraint. Okay. When I say y is greater than equals to 0, then I'm drawing this arrow. It means on the upper hand side. And when I say x is less than equals to 3, you see, this will be the arrow. Okay. Now we have another constraint, which is x minus y less than equals to 1. So you can just think about it as intercept form. So x has an intercept of 1 and y has an intercept of minus 1. I hope you know intercept form of a line. And so that line will be, so it will be at x is equals to 1 and y equals to 1 may be here. So the line will be like this. Okay, so this is the line, this line x minus y is less than equals to 1. For this line, you cannot have an intercept form because the right hand side is 0. And by the way, when I have drawn this, you have to also think about where will this region be, whether the arrow will be in this area or this area, that you have to think, right? So what will we do? We just simply put origin. So if you put 0 comma 0 over here, you just put x is equals to 0 and y is equals to 0. So when you put that, you see you have 0 on the left hand side, and this satisfies that constraint. The right hand side is 1, the left hand side is 0. Therefore origin is on the side which satisfies the constraint. Therefore this region will satisfy that constraint, right? Because over here we have origin and origin satisfies that constraint. So you know that this region is what that constraint is referring to. Okay. Now when I say x minus 2y is greater than equals to 0, you cannot make it in the intercept form because the right hand side is 0. So you can just take the slope of that line and you see it passes through origin. So if you put x is equals to 0 and y is equals to 0, it becomes 0. So it passes through origin. This is the point it passes through, and you can take any other point. Suppose I take 3. So if x is equals to 3 minus 2y is greater than equals to 0, then y will become 1.5, right? So you can take this and it will become 1.5. So at 1.5, so where will be 1.5? Okay, so first we have to see where this it touches here. So what will this be? So if I put y is equals to 3 minus y is less than equals to 1, so 3 minus 1, so this becomes 2. So this point is actually 3 comma 2. Okay, and over here it is touching 1.5. So it is touching somewhere here. So this line, when it starts over here, it touches this point. Okay, now you have to see the region it has. So you cannot put origin because it actually passes through origin. You put any other point. Suppose we are putting 1 comma 1 because 1 comma 1 is on one side of that line. So when I say 1 comma 1, so x is 1 minus 2y, which is also okay. Sorry. When I say 1 comma 1, so for this it will become 1 minus 2 into 1 greater than equals to 0. So you see when I have 1 comma 1, so it becomes 0 greater than equals to 0, it is satisfying. So this point is actually satisfying. So this is the region. This line is actually satisfying that inequality satisfying. Now what you have to do is you have to see what is the region together that satisfies all the constraints. You see over here, this is the region for this constraint, 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 and this is the region for this constraint. The intersection of all this is only this region. You take any other region, one or the other constraint will not satisfy. For example, if you go in this region, so you see this constraint is also not satisfying, this constraint is also not getting satisfied. If you come to this region, so this constraint is not getting satisfied, right? So if you come to this region, then this constraint is not getting satisfied. So only region all the constraints are getting satisfied is the region where I have marked using blue hashed lines, and this region is known as the feasible region. Is that all right? Feasible region. Any questions? Okay. Now you can just obtain this point. Why? Because you see these two lines are intersecting. If you solve them simultaneously, you will be able to obtain this point. Whatever that point is, you can just obtain it. Okay. There is a very important property of linear programming problem, and that helps us solve linear programming problems. What is that property? The property says that the optimal objective function value will be at one of the corner points. So it will either be this point or this point or this point. So in the entire feasible region, you don't have to search for all the points. You see there are infinite number of points in this feasible region. You can take infinite points because it is a continuous region, so you can take infinite number of points in the feasible region. But there is a property which says that the optimal objective function value will be at the one of the corner points. So either this point, either this point, or this point, or this point. So what you have to do to solve this problem, you just take these 3 points, plug into the objective function. Whichever point gives the maximum objective function will be the solution to this problem. So you have just 3 points. So you just plug these 3 points in this objective function. Whichever point gives the maximum objective function value is the solution to this problem. Is that all right? Okay. So this property that the optimal solution is at one of the corner points is the key solution, is the key to solve linear programming problem. So that this is very, very important. Okay. So when we go to higher dimensions, then also we use this idea that one of the corner point will be the optimal solution. So all the algorithms we have to solve linear programming problem exploits this concept that one of the corner points will be optimal. So it moves from, so all the algorithms we have tries to go to corner points. So one algorithm is simplex algorithm. What it does is it moves from one corner point to the other corner point and just checks if that corner point is better or not and whether to go to which corner point next. So this simplex algorithm does that. There is one more algorithm which is known as interior point method. So what it does is it starts with one of the interior points, that is, which is not a corner point, and it tries to move to one corner point. So simplex algorithm, what it does, it starts with a corner points and checks different corner points. Interior point method, what it does is it starts from the middle, but it tries to move to one of the corner points. So that idea that corner point, one of the corner point will be optimal is utilized in both the algorithms. Okay. So over here I have marked, so I have drawn the constraints. So these are the constraints. This is the feasible region. I have marked the feasible region in shaded area, and this is the objective function line, and it crosses to this point, and that is the point which is the optimal point. Okay, that point is that where the objective function is maximum. And I have talked about the algorithms, the simplex algorithm and the interior point algorithm. If you have taken any industrial engineering class, then you might have studied about simplex algorithm. It is a very popular algorithm which is used to solve linear programming problem. And there are standard solvers to solve linear programming problem. You don't have to code simplex algorithm on your own. Okay. So that is why we are not going into depth of simplex algorithm, and this course is not about that part. Any questions on linear programming problems? All right, so we'll move on to the next part, which is integer linear programming problems. So this is one problem, disaster relief problem. This is an example problem. So I'll just ask you to take a minute and read the problem, and then we'll talk about the problem.
It is like snapback problem
Knapsack.
kind of. Yeah, snapback problem.
So I will give others a minute to read the problem. So others, have you recognized this problem? Have we talked about this problem? So this is actually a knapsack problem. So till now we have used meta-heuristics to come to a solution to that problem. Now we will see how to model this problem using integer programming methods or integer programming formulation, and then we will able to use the algorithms to solve integer programming problems to solve this problem. Okay, so this is actually a knapsack problem. There is a transportation vehicle which has some capacity, and this transportation vehicle needs to carry some kits. So those kits are these 1, 2, 3, 4, and 5. 5 kits are there. Each has some specific weight, and the combined weight cannot exceed the transportation vehicle capacity, and each vehicle has some specific value. What are we trying to do? We are trying to maximize the total value of the items while staying within the weight limit of the vehicle. It is the same problem in another application. Okay. So these are the data. So the items are written over here. We have the different rewards and different weights. And this is the capacity of the vehicle, 50 units. Now, before I show you the solution of this, or not solution, before I show you the formulation of this problem, we will approach the formulation in a very similar way. So over here what we did is we tried to identify the decision variable. What is the decision variable? Then we try to identify what is the objective, and then we try to identify what are the constraints. So these are the steps to formulate a problem. Okay, so before going into formulation, you have to follow these steps. You have to specify what is the decision variable, then you can move on to either the constraint or objective function, and then the other. So these two you can interchange. Either you can formulate the constraint first and then the objective function, or the objective function then the constraint. But the decision variable is the first thing you have to identify while when you start formulating a either linear programming or integer programming problem. So can you identify what will be a decision variable for this problem? What can be a decision
The
variable for this?
number of these food packs or medical kits, water bottle. That number means XY.
Medical kits.
Means X means 5 variables. So A, B, C, D, E, F, E.
A, B, C, D, E. So what is the decision variable? So I can say
number of food packs.
So when I say X is equals to 3, it means 3 kits are picked. Which 3 kits are picked? Are you able to identify using this kind of decision variable? So when I use this kind of decision variable, number of kits picked, number of medical kits picked. And if I say X is equals to 3, will I be able to identify which 3? No, right? We will not be able to identify. We can have A, B, C.
No need also. Medical kit means 3 number medical kit is important. That is the information. Correct?
No. Okay, so you are just saying, so you can have, okay, you are saying medical kit. So we have for knapsack problem 1 unit of each. So over here we have 1 unit of each, right? Now,
not
so what
1
will
unit. We are considering, say, food pack is means X number of food packs, Y number of.
When we are talking about knapsack problem, each item has only 1 unit. So over here medical pack has 1 unit, medical kit has 1 unit, water bottle has 1 unit, blanket is 1 unit, and flashlight is 1 unit. You can either pick the flashlight or you can just leave out the flashlight. You cannot have 5 units of flashlight. For knapsack problem, this is how the knapsack problem is. When you're talking about multiple units of each item, it becomes a different problem, which is which we are not talking about. For knapsack problem, it is only 1 unit of that item. Either you pick that item or you don't pick that item. So when I say food packs, it may be a packet of foods, and if you pick that food packet, you have to pick it together. When I say medical kits, it is a combined luggage of medical kits. If you pick that medical kit or you don't pick that medical kit, that is the idea. Okay.
then this will be like A, B, C, D. We can consider food pack, medical kit, water bottle, blanket, flashlight. Then
Right.
my
So
like
it is the
binary kind of things it will be then. Means
yes,
will
it
it?
will be a binary variable. Okay, so we will just label these for our uh, easiness. So we'll say food packet is 1, 2, 3, 4, and 5. These are just labels. So when I say 1, I mean food packet. When I say 2, it means medical kit. And what I will do is I will have a decision variable xi. So I can take values from 1 to 5. It will take value 1 or 0. So when it takes value 1, it means ith item is picked. And when I say 0, then it is not picked or otherwise. Okay. So this is the decision for all I in 1, 2, 3, 4, and 5. Okay. So this is the decision variable we will use. Now, if you clearly see, this decision variable is binary decision variable. And before I move forward, I forgot one thing to mention over here. You see, when we are talking about this Carpenter's problem, you might think that x and y are integer variables, 1, 2, 3, 4, 5, 6, right? Um, it is not actually a real valued problem. You cannot have 1.5 units of table. You cannot have 1.5 units of chair, right? Nevertheless, we are just saying it is real valued. So take an example of another problem. Suppose it is not a carpenter's problem. It is a problem of producing oil. And I'm saying X is liters of oil 1 and Y is liters of oil 2. In that case, it can become real valued 1.2 liter of oil 1, 1.2 liter of oil 2. Why are we formulating this Carpenter's problem as real valued problems? Because it is very easier to solve linear programming problem as compared to integer programming problem. Integer programming problems are many times harder to solve as compared to linear programming problem. That is why I have formulated this problem as a linear programming problem. But this is actually an integer programming problem. It can take value 1, 2, 0, 1, 2, 3, 4, 5, 6, and so on and so forth. It can go to infinity. Okay. So nevertheless, we have formulated it as a linear programming problem. But this knapsack problem, over here we have not formulated it, but the decision variable which we have selected is a binary decision variable. And if you use binary decision variable, it will not be a linear programming problem because it is not taking real valued. So that is one thing to be careful. Now, can you tell me, so these are the decision variables we have. Can you tell me the objective function of this problem? What will be the objective function of this problem? We are having a maximization problem. So I'll write maximize. What will be the expression of the objective function? Think about it. We have decision variables like x1, x2, x3, x4, x5. So if I write Ri times xi and sum over I, that is 100 times x1 plus 150 times x2 plus 80 times x3 plus 60 times x4 plus 40 times x5. If I write like this, will it represents the objective function? It will, right? If we pick object 1, we will have a reward of 100. If we pick object 2, it will have a reward of 150. And since xi can take values 0 and 1, if it is not picked, that reward will not be added. If it is picked, then only the reward will be um, added to the objective function. So we have an objective function, and you see this objective function is linear. Okay, that you have to observe. Now, can we write the constraints? So, Achha, by the way, how many constraints this problem has? What is the constraint in this problem?
the weight capacity.
Yes. So how many
And weight
constraint will have
capacity,
this problem?
it will be having one constant like 15x1 plus 10x2 plus 12x3 plus 8x4 plus 5x5 should be less than 50.
Less than equals to 50.
Less than 50.
Right? This is the
Yes.
only constraint we have, and this is also linear. And there is one more constraint which is actually important, but we have not written here. That is, xi will belong to 0 comma 1. Okay, sorry, 0 comma 1 for all I in this set. Okay, so this is also a constraint that each xi will be either 0 or 1. So this is also one constraint. So we have a knapsack problem has one constraint. So this binary, we just it is a general constraint, so we don't refer it to be a constraint for this problem. Knapsack problem has only one constraint, the capacity constraint. Okay, so this is how the formulation of this problem will be. So you see, the decision variable is a binary variable. It takes 1 if the item is selected and 0 otherwise. The objective function is to maximize this expression. The weight constraint is this, and we have to also ensure that the variables are binary. Okay, the objective function constraints are linear and the variables are binary. Therefore, this is an integer linear programming problem. We generally don't use the word linear, so therefore it is an integer programming problem. But there are integer non-linear programming models. Okay, so if we drop linear, you should you should have this in mind that we are talking about linear problems. Okay, so there are integer non-linear programming models. Okay. But generally, if we say integer programming, we mean integer linear programming. If we are talking about non-linear, we will specify integer non-linear programming. For linear, we try to ignore that linear. Integer programming implies integer linear programming. Okay, is that all right? Now we will see one more example because we have talked about these problems a lot. Therefore, I have taken the same examples over here. Traveling salesman problem. So a traveling salesman problem is a classic combinatorial optimization problem. Combinatorial optimization means that is a combination of cities. The solution will be represented as a combination of cities, right? And actually it is a permutation. You see, the ordering is important, but nevertheless it is known as combinatorial optimization problem. A salesperson must visit a city, a set of cities exactly once and return to the starting city. The goal is to find the shortest possible route that visits all the city and returns to the origin. Input is the set of cities and the distance or cost. It can be cost, distance, time, anything, which we have to minimize. And output is an optimal tour sequence of cities that minimizes the total distance or cost. Okay. So this is the data. This is an example problem where there are 5 cities, and this table represents the matrix uh, specifying the distance between one city to the other. So if I say this, it means distance from city C to city D, which is 30. Okay. So this is the data we have. Now, can you tell me the decision variable? What will be the decision variable?
It can be
Imagine
the
this.
branches.
Sorry, yeah, continue.
It can be the branches means A to B or A to C or A
You
to
are going
D.
in the right. Continue. It might give something.
So the branches may be the decision variable from one node to another node.
So edges, not branches, edges.
Edges.
So how will we write those as decision variables?
So there will be 5 into 4, 20. variables may be there.
Right, so we will have x11, x12, x13, x14, x15, x15, right? That is it. x21, x22, x23, x24, x25, and so on till x55, right? So we'll have xij, where I comma j belongs to 1 comma 2 comma 3 comma 4 comma 5. You can ignore one half of this decision variables. Why? You see, when I'm saying x12 and x21, and no, we have to keep that, right? Because the direction matters. If you go from 1 2 and if you go from 2 1, then those are different things. Okay, so you cannot ignore the half. So yeah, we'll have 5 cross 5 number of decision variables xij. But what this decision variable represent? How will we define this decision variable? So we have some idea that xij can be some kind of decision variables, but we have not specified clearly the decision variable, whether it will be an integer or it will be a real valued or it will be binary. We have not specified it yet. Imagine this as a different problem. Yes, 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 continue.
Decision
I'm
variables can be decision variables can be like a sequence number 1, 2, 3, 4, 5, 6
so
means to total complete 5 cities we need 5 branches.
so when I say that it is 5 numbers, then what is it? It has to be either a real valued or a binary or a integer. Which of the three is that? Is it a sequence of numbers? It is
Sequence of
neither of
numbers.
them. It is neither real valued nor binary nor integer, right? A sequence of numbers.
Yes, yes.
Is that right? Did you understand? A sequence of numbers is not integer. Individual numbers are integer. Sequence of numbers are not integer, right? You can imagine this as a graph problem. So we were talking about graph since the first class. So we have nodes A, B, C, D, and E, right? And currently each node is connected to every other node. So currently we have edges from each node to the every other node, right? Each node is connected to every other node like this. Now, a tour can be thought as whether to keep that edge active or not. So what it means, active or not? You see, when I say A to B is active, then we are traveling that edge. Now, when I say A to D is active, B to D is active, then we are traveling this edge. Oh my God. Then we are traveling this edge. When I say D to E is active, we are traveling this edge. Sorry. Okay, so my pencil lost charge. I don't know if I'll be able to use it. Okay, I'll just explain. So each edge you can think about whether it is active or not. Okay, so when you create one loop, there will be only 1, 2, 3, 4, 5 edges which are active. Other edges will be inactive, right? Is that all right? Right. So if you have something like that, active, inactive, active, inactive, it actually is a binary variable. 1 means active, 0 means inactive. So over here, xij, you can think about xij as a binary variable which takes value 1 if I to j is traveled and 0 otherwise. right? This you can think about as a decision variable.
So that sequence will be considered as constant. Means
No, sequence will be decided when this decision variable values are decided.
so that will be addressed through the constraints.
Yes, so you have to ensure no cities are repeated. So the problem which we were seeing when we are doing crossover, that some cities are getting repeated and some cities are not appearing at all. Those things has to be considered in constraints. That is a constraint, that no city has to be repeated. It should be a complete tour. You cannot have subtours. So if you have subtours, that what does it mean? Over here you will have A, B, E, and again D, C. So this is one subtour, this is another subtour. So over here you are having subtour. So A, B, E, and then you're going back to A and D, C, D, something like that. So it is actually a subtour. So you will have to eliminate subtours. You cannot have subtours. You will have to have a one complete tour of the cities. That you have to ensure in the constraint. Is that all right? Using these kind of decision variables will have this problem. It may create subtours, right? It may create subtours. So this is one example visualization. The decision variable is xij, which is a binary variable, which is 1 if the path from city I to city j is included in the tour and 0 otherwise. What will be the objective function? What will be the objective function?
Objective function will be same as xij into the cost addition, means summation of the xij into the.
So if I say Cij is the cost, that is, this is C12, then we'll have Cij times Xij and we'll sum it over I comma j. So this will be the cost, right? This will be the objective function, and we are trying to minimize this objective function. How are we doing it? So if you are saying A to B, that edge is active, then we have to multiply that edge with the distance, which is Cij. Over here, that is 10. So when Xij is 1, then 10 is added to the objective function. When B to C is 1, then we have to add that 35 to the objective function, right? So this objective function will represent that cost. It will get added. And this subtour elimination is one constraint. There are other constraints also to think about this. You see, when you enter a city, you can enter a city exactly once. And when you exit a city, you can exit a city exactly once. Those constraints also you have to ensure in the formulation. You can enter a city exactly once. You have to leave a city exactly once. Those two constraints and the subtour elimination constraints. If you ensure these three kind of constraints, then the problem will be formulated completely, right? Is that all right? Why are we saying that you have to enter a city exactly once? Because if you enter a city more than once, then you are creating subtours, right? You are entering the city more than once. Similarly, if you exit a city more than once, then you are trying to create subtours. Those are not allowed. You can enter a city only once, you can exit a city only once. Therefore, you will have a that is actually known as flow balance, entering once and exiting once, flow balance constraints. Sorry. So the objective function we have written. So we have written the objective function as Cij times. Just a minute. So we have written the objective function as summation of Cij times Xij, which we have talked about. The constraints, there are three constraints. One is the entry constraints. So what I'm saying is, if this is the node and if this is kth node, and all the cities which can, all the edges which come inside, you have to add. So what I'm doing over here is I am fixing k. I am fixing k and I'm adding over I. So what it is like? So suppose we are fixing city first. The first city we are fixing. So it will be x51 plus x41 plus x31 plus x21 plus x11. All these which are entering 1. 51 means 5 to 1, 41 means 4 to 1, 31 means 3 to 1, 21 means 2 to 1, and 1 means 1 to 1. That doesn't matter. So this summation has to be 1. There can only be one entry, either 5 to 1 or 4 to 1 or 3 to 1 or 2 to 1 or 1 to 1. 1 to 1 cannot happen. So you can ensure that 1 to 1 doesn't happen later. That also you can ensure. Over here I have not labeled it, but you can ensure that xii is equals to 0. That also you have to ensure in the model. Oh, by the way. So I have not written here, but that should be there. xii for all I has to be 0. You cannot have I to I. Okay, that one thing has to be there. And this is the entry constraints. Similarly, this is the exit constraints. So over here we are fixing k, and then we are saying whatever goes out. So for example, x12, so 11 plus x12 plus x13 plus x14 plus x15 has to be 1. And you see, for all k we are doing. So first we are doing it for 1, then we are doing it for 2, then we are doing it for 3. So for all the edges, all the nodes we are doing, entry has to be 1 and exit has to be 1. So these are flow balance constraints. And this is something which is known as the subtour elimination constraints. And I'll give you one example how this flow balance will not ensure subtour elimination. So one example I can give you. So this is A, B, this is C, D, and F. Okay. So you see I can go from A to B and B to A back, and from A C to D, D to F, sorry, not F, E, and E to C. So you see each has one entry and one exit. Each node over here has one entry and one exit. Still it has multiple tours. It has subtours. It is not a complete tour. Right? So it satisfies the flow balance constraint. It satisfies this constraint. It satisfies this constraint as well. But it is not a complete tour. So you have to have a subtour elimination constraints. So for each subset, so over here what it is doing is for each subset. So you can have a subset of 2, 3. You can have a subset of 1, 5. So there are 5 cities, multiple subsets you can have. You can have 3, 2. You can have 4, 1, and you can have 5, 0. So 5, 0 is not true. Okay, so these are the subsets you can have. 2, 3. So there are 2 cities and 3 cities. So a subtour is in 2 cities and another subtour is in 3 cities. You can have, so this you cannot have. 1, 4 you cannot have, because we are saying x11 is equals to 0. Therefore you cannot have this, and you cannot. So for this 5 city problem, you can have either 2, 3 or 3, 2, and both of the things are actually same. So if you consider 3 city and 2 city and 2 city and 3 city, it becomes same. So for this 5 city problem, you only have to consider this kind of subtours, 2 city and 3 city. So there can be multiple situations over here also. So you can have A, B, C, D, E. You can have A, C, B, D, E. You can have A, D, B, C, E. So this 2, 3, there can be multiple combinations. And suppose if this is not a 5 node problem, it is a 6 node problem. So you have to consider all subsets. So this is what it is doing. So for each subset it is saying, so this is one subset and this is another subset. It is saying for each subset it has to have one entry and has to have one exit. So this subset must has an entry and this subset must have an exit. Similarly, this subset must have an entry and this subset must have an exit. And this ensures, so for all subsets you have to do all subsets, all possible subsets. So for all possible subsets, you have to ensure that each has an entry and each has an exit. And if you know about power sets, this will have 2 to the power n number of constraints. If you don't know about it, doesn't worry. But this, the number of subsets of a set, what does it mean? The number of subsets of a set is actually 2 to the power n, where n is the number of elements in the set. So these many number of subsets you can create. So this is exponential actually. This is an exponential number of constraints. And this is the main difficulty to solve a traveling salesman problem, because there are exponential number of constraints. So if n becomes 50, it is 2 to the power 50 number of constraints, and it is very, very high. If you cannot imagine, just try to do it in a computer. 2 to the power 5, 6, 7, 8, it grows exponentially. And that is why traveling salesman problem is one of the hardest problem to solve. It is very difficult to solve traveling salesman problem because of this kind of constraints. We are diverting. So the idea is, this is one kind of constraint, this is another kind of constraint, this is a third kind of constraint, and the other is binary constraints. Okay, and we have to also ensure xii is equals to 0, which I have not written over here. I should have written. Okay, so this is the complete formulation of traveling salesman problem. And if you notice, each of the constraints and objective function are linear, and you have binary variables. Therefore this problem is an integer programming problem. Is that all right? Was I fast? I'm sorry if I was fast.
Then how to solve this problem? Means what is the?
There are nobody has able to give any exact solution method to this problem which can solve large problems. Okay, because this is a category. This belongs to a category of problem known as NP hard problem. So we were talking about classification of problems in our previous class, and you can get approximate solutions. You can be very close. So you can use a heuristic and get a solution, but you will not be able to say this is the best solution for this problem. So there lies the difficulty. You will not be able to say this is the for small problems you can just enumerate and see, but there is no general algorithm which can give you optimal solution to any size problem. I'll repeat again, there is no general algorithm which can give you the optimal solution for any arbitrary n number of cities. Okay, so this is what it means.
So approximate solution is possible. Even that is through which technique? Means
Heuristic we were talking about, right?
normal
Local search, genetic algorithm, you can get good solutions, but you'll not be able to guarantee that this is optimal solution. That word optimal, that is the main problem lies. You'll not be able to say this is the best solution you have for large n's.
Okay.
You can, so you see in general real world we are good enough to work with close optimal solution, close to optimal solution, but theoretically you will not be able to obtain an optimal solution for arbitrarily large n. There lies the problem. Optimal solution, that is the key. You can get good solutions, very, very good solutions using good algorithms. There are good algorithms which will give you good solutions, but it will not say how good it is. Maybe 10% from optimality, maybe 50% from optimality. You will not be able to know. But you have to accept कि हाँ मैंने use किया है heuristic, अच्छा ही solution देगा. Something like that. You will not know कि कितना अच्छा है या फिर ये optimal है कि नहीं है. That is the issue. That word optimality, that is the issue. Optimality means कि this is the best solution you have. There is no other solution which can beat this solution. That is where the problem lies. In real world it doesn't matter, by the way. So I'll not say doesn't matter, it depends upon the application. So if you're talking about like you're doing some space research or very intensive research, like maybe some particle physics or something like that, you would need that guarantee कि कितना दूर है optimality से. But in general managerial problems or something like that, those kind of optimal solutions are not needed. Imagine कि नासा ने कुछ भेजा है स्पेस में एंड this approximation is used, so a little bit of mistake can make the whole plan go, yeah, right? So those areas, these optimality and solutions are required. When you are not, you cannot just say कि चलो काम चल जाएगा.
So this Google map or this whatever the location it used to found, people used to say that they are using the AI. And sometimes, which I don't know whether they are using or not, but whether that those problems are also something like this traveling salesman's problem, I can.
NP hard problems.
Yeah. So now, solving these through this heuristic and solving these such problems through the AI, which is simpler. Yeah.
So what is AI doing, by the way? They are using heuristic. So we have talked about heuristic and meta heuristics. We are doing that because AI uses these kind of heuristics. ऐसा नहीं है कि AI कुछ और यूज कर रहा है और हम फालतू का ये मेटा heuristic पढ़ा रहे हैं आपको. AI are using some kind of heuristics or meta heuristics. It is advanced, but the basic idea remains the same.
Yeah, yes. So my question is, without AI also, all these are possible to solve.
Right. Now,
then why?
Now what I will give you, so you see, without AI, मतलब AI जो इसे technically use होता है, we will get a solution. But what these high level models are doing is they are enhancing these algorithms more. So ये heuristic के साथ कुछ और heuristic combine करके it will try to enhance the solution more. So we have seen some limitations of genetic algorithm and local search, right? You can get stuck in local optima. So what this AI will do is it will try to escape that local optima in some way. So AI, the solution which AI will give will be maybe very close to optima or maybe optimal solution. The problem is we will not be sure कि वो optima है कि नहीं है. हो सकता है कि वही optimal solution हो सकता है कि AI जो solution दे रहा है that is the optimal solution, but we are not sure. Nothing is 100% guaranteed.
But which part of means how the AI will be formulated to come out from that this genetic algorithm, limitation of the genetic algorithm or these heuristic algorithms? So what is the inside of that AI people are doing?
Do is, so we have talked about crossover, mutation, basic crossover operator, basic mutation operator. These operators, there can be multiple different kinds of crossovers. So it will try to optimize at each level. It will try to optimize the crossover operator कि इसको और अच्छा कैसे कर सकते हैं. It will try to optimize the mutation कि इसको और अच्छा कैसे कर सकते हैं. It will try to optimize the parent selection कि क्या best parent selection हो सकता है. It will try to optimize population size कि what should be the best population size कि मेरे को कम टाइम पे भी एक अच्छा सोल्यूशन मिल जाए. व्हाट शुड बी द नंबर ऑफ जनरेशंस. ये सब चीज टेक्निकलिटीज जो छोटा छोटा चीज हम लोग मिस कर गए हैं, those technicalities are refined and refined and refined, and there are multiple modifications of genetic algorithm. So those modifications and higher level genetic algorithms are used. Basic idea will remain the same.
So can we consider that these artificial intelligence based algorithms are extended version of these heuristic algorithms?
So you see, when we are talking about artificial intelligence, you will not be able to say what are they using because they use neural network. So when they use neural network, those are actually using machine learning. So क्या करते हैं ना कि उसमें इस तरह से solve नहीं करते हैं. उसमें करते हैं क्या कि they see past data, and from that past data they try to learn कि what are the solutions we have, and they try to modify those solutions using neural network. So over there that technique is little bit different, but the solution will be, मतलब आप सबको solution मिल जाएगा, right? So over there they uses past data. आप AI कितना भी पढ़ लीजिए, there has to have input data. अगर input data नहीं होगा तो machine learning AI कुछ नहीं कर सकता. It learns from data. And this meta heuristic which we are talking about, you see, अगर analytics में जाएंगे ना, so there are multiple levels of analytics. First is मुझे levels अच्छे से याद नहीं है, but I will tell you. One is predictive, prescriptive, or descriptive. So one is descriptive analytics. The descriptive analytics is when we are trying to understand the data, like mean क्या है, median क्या है, forecasting थोड़ा सा कर लिए. So that is descriptive analytics कि आप data को देख के describe करने की कोशिश करें कि what is the data all about. The other level is predictive analytics, जहाँ पे आप predict करने की कोशिश कर रहे हैं. So you have past data. Machine learning जो करता है, it has past data, it takes the input and it tries to predict कि next month का sales क्या होगा, next month का प्रोडक्शन आप कितना करिएगा तो इट विल हेल्प यू. सो इट इज प्रिडिक्शन कि इतना आपका सेल्स हो सकता है, इतना आपका डिमांड हो सकता है, एंड सो ऑन एंड सो फोर्थ. उसका ऊपर आता है प्रिस्क्रिप्टिव एनालिटिक्स. सो ऑप्टिमाइजेशन इज एक्चुअली प्रिस्क्रिप्टिव एनालिटिक्स, एक स्टेप ऊपर है मशीन लर्निंग से. सो व्हेन वी टॉक अबाउट मशीन लर्निंग, इट इज बेस्ड ऑन ऑप्टिमाइजेशन. वी विल सी जब हम लोग मशीन लर्निंग पढ़ेंगे, इट इज द फंडामेंटल इज एक्चुअली ऑप्टिमाइजेशन. मतलब मशीन लर्निंग का आइडिया ऑप्टिमाइजेशन से आया है. ऑप्टिमाइजेशन क्या करता है, ट्राई टू प्रेस्क्राइब कि अगर आपका, सो इफ मशीन लर्निंग हैज गिवन यू दिस डिमांड फोरकास्टिंग, you have to have this kind of operational challenges. अगर आप meet कर लीजिएगा, then only you will be able to meet that demand. So it is prescribing. So for example, it will say कि you have a facility and machine learning predicted this D1 data demand. Now what you have to do is you have to hire more laborers such that you will be able to meet that demand. Moreover, that will maximize your revenue. So it is prescribing. Machine learning is predicting and optimization is prescribing. So three levels of बीच में और एक लेवल है, I have forgotten, but these are the main levels: descriptive analytics, predictive analytics, and prescriptive analytics. Optimization comes on prescriptive analytics. It prescribes. और मशीन लर्निंग का मोस्ट ऑफ द आइडियाज ऑफ मशीन लर्निंग हैज कम फ्रॉम ऑप्टिमाइजेशन. एक ऑब्जेक्टिव फंक्शन रहता है, जनरली वहाँ कंस्ट्रेंट्स नहीं होता है. वी आर ट्राइंग टू ऑप्टिमाइज, ऑब्जेक्टिव फंक्शन को मिनिमाइज करने का कोशिश करते हैं. एंड इफ यू हैव स्टडीड समवॉट मशीन लर्निंग, यू विल रियलाइज वहाँ पे मीन स्क्वायर्ड एरर आता है. वी आर ट्राइंग टू मिनिमाइज दैट मीन स्क्वायर्ड एरर. अगर आपको नहीं पता, वी विल टॉक अबाउट इट इन आवर क्लासेस and we will see that that is an objective function, and what machine learning is trying to do is trying to minimize that mean squared error, and उससे वो predict करता है. I don't know if I have answered your question or not, but बहुत सारा चीज हमने बात किया.
Yes. Now we shall study some AI ML also in this course.
Yes. Without that AI कैसे होगा? We will have to go to machine learning and then neural networks. Otherwise this course is not AI. This course is just optimization and everything. So we have to go to machine learning and deep learning and then maybe natural language processing, and over there we will see कि optimization क्यों important है machine learning के लिए.
So what you said, that probably constant probably inside that network, maybe by default the constant are model within that neural network itself, so that whenever input we are giving and that is passing through that neural network, whatever the output is giving, the final output means prescription, what you said, that maybe inside that network, maybe all automatically by default the constant are being used to model that network. Can it be like that? I don't have any knowledge apart from the students used to present some here and there. They used to present the.
No, when we do machine learning, so उसमें क्या होता है, there are data available. So what it does is it try to fits a line on that available data, and that line is such that whenever we have new predictions, the error from that line, so ये हम लोग linear regression का बात कर रहे हैं, so that line से जो error आएगा prediction का, it tries to minimize that. We will see.
So following a line itself is something like a constant. Can we not think in that way? This following a line itself is like a constant. When whatever this today we did, that straight line means this whatever you did, region area you considered, this following a line itself is a constant.
No. These are different problems. Now, machine learning you have data. That data that doesn't specify some constraint. Machine learning will not specify this data has some constraint. It will give you the data. This is what it is. You try to identify what is the objective function. Machine learning objective क्या है? It gives you data. कि this is the data I have. You try to specify what is the objective function equation. The equation of the objective function we are trying to get. मतलब how will I tell you कि nature ने कुछ किया है past में, and we are trying to see कि nature कौन सा function को minimize कर रहा था. We are trying to obtain that function. If we get that function, then we can make predictions कि okay, next अगर ये input है तो because that is the input, ये function के हिसाब से this is the output. So we are trying to predict that function. the objective function which that data is trying, उल्टा कर रहे हैं, we have data, we are trying to get the function. यहाँ पे we have a function, we are trying to get इसका minima क्या है, maxima क्या है. We will see.
Okay.
We will see.
Yes, yes. And okay. So this month, how many lectures will be there? All will be on Sunday itself?
No. So there is one issue. From next Sunday, I'll not be available for 15 days. So what I'm planning is to have one lecture on Tuesday and one lecture on Saturday.
And then after that, next
after 15th, I will let you know when will be our next class. And during that time, you can work on your project. I will inform about the project as well.
Okay.
Any more doubt? Okay, so let me see what I have. Yes. So algorithms to solve integer programming problem will not go into this because this is higher level optimization theories. We will just name these algorithms. This is branch and bound, branch and cut, cutting plane, and heuristic and meta-heuristics we have seen. So we can use heuristic and meta-heuristics to solve these problems. But these are exact algorithms. This is approximate algorithms. That is the difference. These are exact algorithms. It tries to get the exact optima. Okay. So we have seen, yeah, conclusion mein ho gaya. Okay. And optimization mein, there is one part which is remaining, which is known as constraint satisfaction. We will see that in the next class, and then we'll move on to machine learning. Okay. All right. Thank you. Thank you for joining.
Thank you, sir.
I'll end the meeting now.
Thank you.